Concorde first flew in 1969. 30 years later, she was still the world's only supersonic airliner. There had been many rivals to her crown, but they quickly faded away. And despite her age, she never failed to win new admirers. It was not just her awesome speed, but also her elegant, purposeful lines that stirred so many souls. But Concorde's beauty was not the result of an artist's fertile imagination, but years of diligent scientific study and research that pushed back the boundaries of our understanding of flight. Today's airliners have a Mach meter on the flight deck, showing the aircraft's speed compared with the speed of sound, or Mach 1. But in the early days, the sound barrier of Mach 1 was a mystery. No one knew quite what would happen as an aircraft approached Mach 1. Early trials gave some ideas. They showed that as an aircraft nears the speed of sound, shock waves develop at the leading edges of the structure. The thin boundary layer of air is heavily compressed. Drag increases. Control surfaces can vibrate madly. The whole aircraft could become unstable and even break up. In order to fly faster than the speed of sound, aircraft would need to be designed with a completely new wing shape that delayed the effects of air compressibility. Much of the early research into aerodynamics was carried out in Germany during the Second World War. One of the fruits of their work was the Messerschmitt Me-262, which, apart from being the world's first jet fighter, had a gently swept wing. After the war, many of the German scientists found new employment in America, Britain, and France. One of the first British aircraft to benefit from this research was the Handley Page Victor, which first flew on Christmas Eve 1952. The Victor had a swept wing shaped like a crescent. This compound swept wing was designed to delay compressibility effects up to high subsonic speed, although a Victor did on one occasion, and unofficially, fly supersonic. Another development was the delta wing, which first appeared on the Avro Vulcan bomber. With its 4 powerful turbojets, the Vulcan first flew in August 1952, nearly 2 decades before Concorde. 1954 was the year when British test pilot Roland B. Beaumont exceeded the speed of sound in the new ultra-fast English Electric Lightning. Two years later, another Briton, test pilot Peter Twiss, set a new world record of more than 1,800 kilometers per hour. His Fairy Delta II experimental jet, with its wings swept at 60 degrees, also sported the first droop snoot to improve forward view at takeoff and landing. Experience led to even smarter designs. The Saab Draken featured a very distinctive wing. It was a cranked double delta shape, its outer section swept at 80 degrees. The French too were busy with delta wings. The Mirage 3 proved highly successful. Its maker, Dassault, liaised with Fairy to develop an even smarter wing for the Mirage 3A. It reached Mach 2.2 as early as October 1958. The Mirage 4 was intended to be a light bomber and was designed to fly at twice the speed of sound. It was also stable at much lower subsonic speeds. Another bold French design was the Durandal, an experimental supersonic jet. Its shape was designed to fit inside the shockwave from its nose intake. Its behavior in the air made its pilots call it the Flying Slab. Pierre Sartre, its designer, also masterminded another great success, the Caravelle airliner. Later on, he worked on Concorde's development. In April 1960, France began its first studies for a future supersonic airliner, seen here in its wind tunnel testing. Meanwhile, in Britain, aerodynamic research continued. The Handley Page 115 was another strange-looking but even more useful experimental design. Designers needed to gain clear, practical knowledge of how high-speed Delta airliners would fly at low speed. So this low-speed research plane, with a wing that could be fitted with leading edges of different sweep, proved crucial in the development of Concorde. One of the problems of supersonic flight was the effect of heating on the aircraft's structure. The Bristol 188 was built to test the kinetic effects of supersonic flight. Late in November 1962, France and Britain signed a deal to develop a civil supersonic aircraft together. It led to lengthy negotiations. There'd never been such a big development deal between two different countries with two very different traditions. In the end, they agreed on details of who would undertake design, development, and production, and there was no cancellation clause. 4 leading aerospace companies would handle the program. Aviation and BAC would build the airframe. Bristol Siddeley, later to become Rolls-Royce, and Snecma of France would develop its mighty Olympus engines. Meanwhile, the Americans didn't want to be left behind. They too proposed new supersonic transports, or SSTs. Lockheed planned an SST that would fly 150 people at 3,000 kilometers per hour. And Boeing launched a program to develop an SST that was just as fast, but big enough for 250 people, and built in titanium. 4 General Electric engines would produce 23 tons of thrust. But these were only proposals. In Europe, a real program was now underway. Development of Europe's first SST needed to cover much new technical ground. Research laboratories investigated fuels, lubricants, paint, plastics, metals, materials, and hundreds of other challenges. Materials for the new plane structure were put through intensive trials for 24 hours a day over 18 months. The effects of heat and pressure on new adhesives were another priority. New metal-to-metal bonding techniques were developed. At its peak, Europe's SST research involved 600 companies and nearly 200,000 skilled workers on both sides of the English Channel. For the two nations, it had become a new and exciting challenge. Another experimental aircraft that played a major part in SST research was this Bristol 221. It was a rebuilt version of the Fairey Delta II record holder. Its job was to confirm the high-speed behavior of a new, refined type of delta wing called an OG wing. In theory, this type of wing could give the new SST the range and payload it needed. In practice, the only way to find out for sure was to build a flying testbed. Another vital factor for the new SST would be its power plant. A supersonic version of the Bristol Olympus engine had been developed for Britain's new and advanced bomber, the TSR-2. But defense cuts in the mid-1960s scrapped this highly promising new bomber. Luckily, its engine proved the ideal basis for developing an even more powerful Olympus for the SST. Meanwhile, wind tunnel tests helped to define the new airliner's optimum shape. The aerodynamic behavior of the new OG wing looked promising. Vortex patterns in the wind tunnel confirmed the wing's potential. These trials worked out the effects of different angles of attack on airflow across the wing. They also helped to define the position of the aircraft's engine nozzles. All 4 engines would need free, unhindered airflow at all speeds to work efficiently. Sud Aviation in France focused on parts of the structure shown here in yellow. Many of these parts would be made on the first numerically controlled milling machines in Europe. Again, the SST was lifting Europe's technology to new heights. Nearly 20,000 test cycles proved the strength of Concorde's landing gear, which was designed in France. A full-scale mock-up was built to help confirm the shape and fit of all the SST's components. In the days before electronic design on screen, this was the only way to make sure the airliner's 240 kilometers of electric wiring would fit and function properly. Sections shown here in red were the task of BAC, the British Aircraft Corporation. BAC engineers built a mock-up of the flight deck as well to help confirm the radical new drooping nose would work in practice. This droop snoot was essential to give the flight crew enough forward vision at takeoff and landing. All major structural items went through highly intensive fatigue tests. Here we can see how a forward fuselage section was immersed and pressurized at Sud Aviation's works in Toulouse. Structures also suffered massive extremes of heating and cooling in test chambers. They helped work out the new airliner's expected fatigue life. Rear fuselage sections and the tail fin were built at BAC's workshops in Britain. Units were shipped to and from Toulouse and Bristol to give each country its own final assembly line. Each centre became a source of extreme national pride. One of the biggest challenges of all was the development of power plants. After 4 hard years of research, development and ground trials, the first Olympus 593 was test flown in a converted Vulcan bomber. Like all jet engines, the Olympus could only work efficiently when it received air flowing at subsonic speeds. So for flight at twice the speed of sound, a complex system of inlet doors and ducts were needed in the intakes to feed the Olympus with smooth air at subsonic speed. A whole new design of exhaust nozzle was required to ensure the massive thrust of the Olympus was used most efficiently. This pioneering design worked almost perfectly. It also carried special ducts called buckets to provide reverse thrust to slow the aircraft after landing. Final assembly of the prototypes of Europe's SST, now named Concorde, began in April 1966. Major sub-assemblies travelled between plants in the 2 countries by air, road and ship, often on specially designed trailers. wide loads became familiar sights on roads around Bristol and Toulouse. Royal Air Force Belfast transports were recruited to airlift sub-assemblies. At both final assembly plants, the new SST came together with the highest standards of accuracy. Tolerances were tighter than ever before. At last, the two prototypes neared completion. The sleek new pride of France and Britain made its first appearance at Toulouse in December 1967.
But the rollout in December 1967 was perhaps the most emotional moment for me. For the first time, we saw the aircraft in its entirety, without scaffolding, painted, and we could appreciate its true size outside the hangar. And it was at that moment that its beauty, although it was to be further perfected in production aircraft, impressed us all. And I think the same is true for all the different flight crews that were to be responsible for flying this aircraft, which was the fruit of millions of hours of work.
But Concorde also had a rival. It came in the surprisingly familiar shape of the Tupolev Tu-144 from the other side of the Iron Curtain. At once it gained the name Concordski. This was the Cold War, and Russia was desperate to go one better than its European rivals. So the Tu-144 was designed to fly marginally faster than Concorde at Mach 2.2 and to fly that little bit further, as far as 6,500 kilometers. The Russians even scored by getting the 144 airborne before Concorde, but that was about the only time Concordski ever edged in front of the Anglo-French project. Much more threatening competition came from another direction, for in the same year that Concorde made its first flight, another distinctive shape took to the sky. Boeing's giant newcomer, the 747, soon made its presence felt. Concorde's makers watched with concern as Britain's own national airline, BOAC, became one of the 747's launch customers. Boeing's rivalry with Europe's aerospace industry grew even more intense. But technologically, Concorde was far ahead of the big Boeing, and far faster. By March 1969, Concorde was cleared for takeoff at last. At 1500 hours on March the 2nd, 1969, in Toulouse, Chief Test Pilot Andrei Turka released the brakes of prototype 001. With engines on full reheat power, they made a thunderous, glorious noise. With the whole world watching, Concorde 001 and the hopes of a new Europe took to the air. Turka kept the undercarriage down for this first slow but vital flight. On the flight deck, every last detail of the prototype's performance was monitored and logged. It proved a perfect first flight. The world's most advanced, most exciting aircraft had flown at last. It made a perfect landing. From this moment on, Andrei Turka's name rang around the world.
But that aircraft had fixed geometry air intakes. The air intakes were to direct inlet air towards the engines and reduce its speed from supersonic to subsonic. The intake regulation systems were not yet ready, and we had to fly with fixed inlets, which reduced the scope of our tests.
It's It's April the 9th, 1969, and Concorde 002 is ready for her maiden flight from BAC's airfield at Filton. As in Concorde 001, no passenger seats, but 12 tons of flight test equipment. Today, the six-man crew was led by Brian Trubshaw, Director and General Manager, Flight Operations, BAC Filton, together with his co-pilot, John Cochrane. Of thousands of people concerned with the production of 002, few have awaited this moment more eagerly than those whose job it is to finally prove the aircraft in the air, the flight test crew.
The great day was interesting, to put it mildly. I'm very excited because we'd had 2 days of frustration with the failure flag on the first pilot's airspeed index popping up every time we did a taxi run up above 80 knots. And after about the third go to fix it, I said to the engineers and the designers, well, if it works this time, we'll go. We're not going to come back and tell you it's working. Unfortunately, it was, and off we went.
Concorde 002 is clear takeoff, and good luck, gentlemen.
Fingers crossed. Il roule. Nous croisons les doigts. Full power and reheat.
At this point, Brian Trubshaw decided to turn a high-speed taxi run into a first flight.
Hey. So obviously the ASI is all right. Merveilleux.
Understand working control. 02, you're clear to land from this approach.
Well, on an aeroplane where the pilot's eyes are very high off the ground when the main wheels touch, you need to be aware of the height quite accurately. And you use radio altimeters for the last, say, 100 feet or so. And they're called out either by the co-pilot or the flight engineer, in the case of the Concorde. And we were denied their accurate information on our first flight because they both failed during the flight from Filton to Fairford. It wasn't too bad. I think we arrived about a quarter of a second early.
After a 22-minute flight, Concorde 002 landed safely at the Royal Air Force Airfield at Fairford in Gloucestershire, the British base for Concorde flight operations. After years of careful study and dedicated attention to detail, here was another thrilling and rewarding climax for the thousands of men and women working in the factories of British Aircraft Corporation and Sud Aviation, in the knowledge that the British-built Concorde flew just 5 weeks after her sister 001, and that 2 Concordes are now flying. Brian Trubshaw said the flight was cool, calm, and collected, and that the crew enjoyed it immensely.
Now, with 2 prototypes flying, development work could press ahead twice as quickly. At Farnborough, a full-sized test aircraft was already well into intensive trials. Its job was to soak up all the structural punishment a real Concorde could expect in 1.5 lifetimes in service. At Toulouse, a similar airframe underwent a grueling series of static tests to simulate the effects of extreme heating. Concorde was entering new territory. Tests were crucial to the program's success. Fatigue tests showed the structure could stand up to massive stresses. They also proved its ability to cope with repeated heating and cooling during supersonic flights. Landing gear showed it could withstand heavy overloads. Concorde's fuel tanks were designed to help trim the aircraft at different stages of flight. Fuel could be pumped from one tank to another to adjust the trim to just the right angle of attack for different Mach numbers. Engineers gave each prototype a thorough check after every flight. Pre-flight preparation too had to be rigorous. Nothing could be left to chance or improvisation. Each Concorde was a flying laboratory, crammed with instrumentation and measuring equipment. They brought more knowledge and more confidence with every flight. Airborne tests proved this big new airliner could fly almost like a fighter. It was responsive, hugely powerful, and fast. Even at low airspeeds, it proved impressively easy to fly. Flight trials continued apace. Within just 6 months, each prototype had logged 120 hours of flying. This was good going for a pioneering high-tech project of such complexity.
Vibration tests had opened new vistas in terms of pure speed. Now we had to increase speed, and with the variable geometry air intake systems, during the 1970s we were to make progress. With great prudence, but for different reasons, because we were worried about the possible effects of an engine cutout, or the cutout of two. The Americans had had many a problem in this field. Their bomber B-58 Hustler had crashed several times at Mach 2 and had had accidents due to engine breakdown.
You had to operate the aeroplane to get the maximum range, obviously, and in so doing, it meant that you operated the engine as near to what's called the surge line as you dared. And getting the margins correct, which meant tinkering with the intake, was quite a drawn-out performance, and it went on right through the whole development program.
So we went carefully, step by step, and were pleasantly surprised to find that aircraft handling was good up to Mach 2, and that even with 2 engines out on the same side, the pilot still had several seconds, which is a long time, you know, to regain control of the aircraft.
For these men, flying at twice the speed of sound is part of the daily routine. Mach 2, about 1,350 miles an hour, or slightly faster than the muzzle velocity of a .303 rifle bullet. Mach 2 is now routine.
Then we were not only concerned to test fly at high speeds, but also at low speeds, to allow for landings under normal conditions. In other words, landing at higher angles of attack than would ever be used by normal aircraft. These were exciting tests. First, we tested straight landings, then simulating a sudden obstacle in the line of approach, another aircraft crossing our path, for example, simulating avoidance techniques. So we tested increasingly violent maneuvers at different approach speeds and increasingly brutal avoidance maneuvers. And then we decided to push the aircraft to its limits with the most violent maneuver possible, and I saw the angle dial increase. We had a small indicator of angle of attack, and the needle began spinning like a ventilator, and I realized that we would have to react quickly if we were not to put the aircraft at risk. The aircraft responded well. We had gone far beyond the conditions for which the design office had guaranteed the safety of the aircraft. All we had to do was to develop a better safety system, so that today it is impossible for the pilot to go beyond certain danger limits, even if his avoidance measures are violent at approach speeds.
Steadily, patiently, tests of the two prototypes opened up Concorde's flight envelope. Speed and height proved to be relatively easy parts of the design to achieve, but a third factor, range, was just as important. For without enough range, Concorde could never enter service to carry airline passengers. Concorde also had to fit in with conventional, much slower aircraft. Its speed of approach to airports and its ability to fit in to normal approach patterns were essential. Then Concorde began to make international flights. Its first was to Dakar in Senegal. Concorde also became a new favourite at air shows and demonstrations. Officials from many leading airlines took their turn to visit, to look, to see, to fly. They were impressed by Concorde in so many ways. But one big concern still remained: Concorde's range.
Then after this flight to Dakar, we thought that the best destination for the aircraft was the aerospatiale route to South America, to Rio de Janeiro or Sao Paulo. But the prototype didn't have that kind of range and couldn't cross the Atlantic, not even the South Atlantic. So we stopped off in the Cape Verde Islands so as to shorten the South Atlantic crossing, and from there flew to Cayenne. And from Cayenne, we flew what I would call almost a sea route over the virgin Amazon rainforest to Rio de Janeiro and Sao Paulo.
But then, to the immense relief of Concorde's builders, the first deals were signed. British Airways ordered 5 Concordes and Air France 4. By 1970 standards, the asking price of $31 million was immense. Rival airlines backed off, although some, like China's national airline, continued to show interest. In theory, the world's airlines still held options for more than 70 Concordes. BAC and Aerospatiale continued to fly Concorde around the world. The whole world wanted to see this remarkable new aircraft.
002 has done its share of VIP flights. Australian government representatives go aboard to learn at first hand what Mach 2 is going to mean to intercontinental travel.
Australia, though, also saw some of the early protests against supersonic transport. People were starting to get worried about its noise, its heavy fuel consumption, its sonic boom, and its emissions. In the United States, Boeing realized that the problems of noise, pollution, and pure economics were compelling reasons to abandon its SST program. Privately, Boeing officials admitted their design still carried major technical problems that threatened its promised range and payload. It was just too ambitious to become a reality. Meanwhile, the Concorde program cruised on. Britain and France together agreed to build 16 production standard aircraft. These were bigger and more capable than the 4 prototype and pre-production models. Power plants too were improving. By now, Olympus 593s were virtually smoke-free and highly reliable, even at the continuous full power rating required for cruising at twice the speed of sound. Production moved into top gear at Toulouse and Filton. New, enormous transport aircraft called Guppies helped move large Concorde sub-assemblies between factories in Britain and France. Before Concorde could earn its ticket to enter airline service, still more trials were needed. Water ingestion tests on the Olympus engines showed that the world's most powerful turbojets could cope with huge amounts of rain and spray. Engines and airframes alike had to show they'd work reliably at extremes of heat and cold. Here at Fairbanks, Alaska, Concorde proved perfect at temperatures as low as minus 45 degrees centigrade.
Things change below minus 30 degrees. You can't just go around as before. You have to be protected constantly, your nose, your ears, etc. Then there were small problems with the aircraft. But they were minor problems. After having abandoned the aircraft for 36 hours, that was the rule, for 36 hours at minus 45, we returned. The first problem was getting into the aircraft. The door was stuck. Then the second problem, inside the cockpit, the temperature was minus 27. But in the end, we were going to have to welcome passengers on board, and we couldn't welcome them at minus 27. Second test, heating the cabin. We had to make a last-minute change. We couldn't tow the aircraft, as a plug had been put into the hole where the hook goes, and we couldn't get it out. We had to blow hot air onto it for 2 hours before being able to pull it out. Making the original hole just a bit bigger allowed us to solve the only real problem we had under freezing conditions.
In warmer climes, Concorde flew its proud flag on the Pacific coast, and in Mexico, where prototype 002 won a tremendous reception. At Mexico City's airport, 2,000 meters above sea level, Concorde coped easily with the heat and the thin air. The SST's reception in San Francisco was more nervous. Americans could reach the moon, but they'd backed down from developing a competitor to Concorde. Their nervousness was understandable. Prototype 002 flew the world. Anchorage and Los Angeles were just two airports of call. In South America, the intense global sales effort went on. In 1975, with Concorde now in the production phase, the whole program got another big lift. Concorde received its full certificate of airworthiness. At last, Concorde was cleared to enter service and to carry fare-paying passengers. Two cabins accommodated 100 passengers, served by 2 galleys. Travel agents were overwhelmed with applications for tickets. High prices, typically 20% above subsonic first-class fares, didn't put people off. Imminent arrival in airline service also brought a new phase of crew training for airline personnel. The clear air and steady weather of Dakar in Senegal made it an ideal airport for training airline crews. Takeoff after takeoff proved the point that Concorde's makers had stressed right from the start, that Concorde would be just another easy aircraft to fly, easy to fit into airport arrival and departure schedules. And then, early in 1976, Concorde's big moment finally arrived. Its first scheduled flights with fare-paying passengers. 2 production aircraft took off simultaneously, one from Paris, one from London. It was a double moment of triumph, a new era in air transport, a tremendous success for its designers and for technology. One was bound for Bahrain, the other to Rio de Janeiro. Supersonic flight now became an everyday event for passengers, complete with a special Concorde stamp. After intense lobbying by Britain and France, the US agreed Concordes could land at Washington. And from November 1977, the US cleared Concordes to use New York Airport too. And so began a transatlantic success story that was to run for 25 years. Concorde's supersonic flights soon became routine. Reliability, punctuality, and above all speed proved just what the top of the market demanded. Meanwhile, Concorde's much vaunted Russian rival was running into bumpy weather. Crude by comparison, the Tu-144's airframe and systems couldn't easily cope with flight at Mach 2. Worst of all, its engines couldn't provide enough power for supersonic cruise without running continuously on reheat. This meant their fuel consumption was enormously high. In turn, its range fell far short. After a few token months in Russian national carrier Aeroflot's service, flying the mail, Concordski quietly disappeared from the airline scene. 12 production 144s were built, but few entered service. 2 pre-production aircraft also crashed. Russia's entry in the supersonic transport race faded into disuse. Concorde now stood alone, the undisputed world leader. Concorde's scheduled services became part of those airports' daily routine, although even the most seasoned travellers and spectators could never fail to feel a little excitement every time Concorde flew. But behind the scenes, nothing was taken for granted. Pre-flight preparations were thorough and painstaking. With passengers paying well above first-class rates, they expected everything to be perfect. Routine scheduled flights were just one aspect of Concorde's working life. Records were set, such as enabling passengers to witness 2 sunrises in one day. In another stunt, she flew around the globe in just 32 hours. But Concorde's sonic boom meant it could not fly supersonically over most countries, restricting its usefulness to routes over oceans. Compared with more modern airliners, Concorde was costly to keep flying. It was an aircraft born of the 1960s, when aviation kerosene cost just a few cents a barrel. And the fuel crisis of 1974 more or less put the brakes on any other sales of the aircraft. So only Air France and British Airways put Concordes into service. Concorde's public loved every moment. The sleek airliner stole the show every time it appeared. In Toulouse, the world celebrated the 20th anniversary of Concorde's first flight with true French flair. And Air France Concorde even got a special paint scheme. Many of the programme's outstanding leaders received their ovation too. Britain's chief test pilot in the early days, Brian Trubshaw, celebrated again with his French counterpart, André Turcat.
So over the many years of design and development, we tried to create an aircraft where the passengers would feel comfortable, but where the pilot would feel happy too. So, now you must tell us what you think of this aircraft that we delivered to you on the 21st of January 1976.
Well, I started flying it later, but I must say that as far as I'm concerned, it's an aircraft that surprised me. It surprised me by the way it handled and by its quality in general. It's an extremely sensitive aircraft. Its intelligence surprised me. You spoke of the help you tried to give the pilot, and in high-altitude flight, I must say that the automatic pilot is remarkably intelligent. This aircraft can fly at high speed, at high temperatures, it climbs fast, it loses height smoothly.
We did our best.
So on the whole, it surprised me.
Concorde is a wonderful example of what you can achieve, sometimes in spite of politicians, if you really mean to. I mean, nobody thought that such a complex project could be made to work the way Concorde has worked. And it did work because nobody was going to allow it to be a failure. I think everybody that was involved on both sides of the channel were tremendously proud to be in it, and consequently they got on with the job. Every now and again somebody interfered at the top, but it happens, and it shows you what you can do. But you have to have determination. You have to see the other person's point of view sometimes. You have to have a level of understanding. But above all, it's the determination that this is what you want. The Concorde has had a big bearing, in my view, on the very successful formation of Airbus industry. And Airbus industry has become, and will always be, a great competitor to the American aircraft industry, which up to the arrival of Airbus industry was dominating really all of the civil world.
For nearly 30 years, Concorde enjoyed a relatively trouble-free life. But on July the 25th, 2000, tragedy struck. An Air France Concorde taking off from Charles de Gaulle Airport outside Paris crashed. There were no survivors. Debris on the runway had caused a puncture, but as the tire disintegrated, it ruptured a fuel tank, engulfing the port side in a catastrophic fireball. The loss of life was tragic enough, but the accident also resulted in a crisis of confidence in the aircraft. The entire Concorde fleet was grounded. There were some who felt that maybe it was time to retire Concorde. After all, she was 30 years old, and other problems were beginning to appear. But in the end, it was decided to make the necessary modifications, despite the enormous cost. In November 2001, Concorde returned to service. But by now, the world's airlines were facing financial crisis following a downturn in passenger numbers that not even Concorde could change. After barely 18 months, the painful decision was made. Concorde was to be grounded, this time for good. On October the 24th, 2003, Concorde lifted off the runway at John F. Kennedy Airport, New York, for the last time. Thousands gathered at Heathrow to greet her and two other aircraft. In the weeks that followed, the fleet was dispersed, with the aircraft going to museums. The most poignant delivery flight was Concorde's homecoming on November the 26th to Filton, near Bristol, from where the British part of the Concorde story began so many years ago.